Okay, so last time we had talked about this invariant of a sheaf, I of F, which is the alternating sum of the dimensions of the sheaf cohomologies. And if my scheme is projective, then I should say projective over K, then the dimension, I should just say HIF, is always finite, and only finitely many of these are non-zero. So for, I should say, X is projective over K, and F is coherent. Of course, there are quasi-coherent sheaves where you do a dumb thing like take infinitely many copies of the same thing. That's a perfectly good quasi-coherent sheaf, and then this will be infinite. But if you have a coherent sheaf on something projective, this is finite dimensional. Maybe at some point we'll prove that. Sort of a nice theorem because you prove by downward induction that it's finite. So if you wanted to prove that sections are finite dimensional, it's actually easier to prove that by proving first that Hn and then Hn minus 1, Hn minus 2 are all finite dimensional. All right, cool. So we've been talking mostly about smooth curves. Oh, that's 1D. Hey, varieties. And usually we've been assuming that they're proper. Sort of makes life a little easier. All right. And in this case, this chi is something very simple. If I look at I of O of D, right, one of the nice things about being curved, divisor just means a finite number of points with some coefficients. The sum of those coefficients is the degree. And so since they're only non-zero homology in 2 degrees, this is just the difference of the dimension of H0 and H1. And we saw at the end of class last time that when I change this divisor, I change this number by 1 when I add a point to the divisor, and I subtract 1 when I remove a point from the divisor. So this Euler characteristic is the degree of the divisor plus some invariant that's the same for all line bundles, which is chi of the structure sheaf. And by definition, this is 1 minus G. So what I'm doing here is the genus is, for my purposes, defined to be H1 of the structure sheaf. Right? As mentioned before, this is what's called the arithmetic genus. Because for singular curves, there's a different notion of geometric genus, which is different, but for smooth curves, it's the same. All right. Any questions? And this is just for simplicity, assuming everything is proper. No, because if you right? If you do a base change, no, uh, it's not going to depend on K at all. So the arithmetic part isn't like about changing the base field. It's about like, it's defined in terms of like dimensions of these spaces of sections rather than a geometric property of the underlying scheme, right? Um, you know, right? The way that we would probably think about geometric genus is, well, we think about a complex curve, and then the underlying space with its complex topology is a two-manifold, and the genus is the number of holes. Yeah, if I take H1 of, um, yeah, X with coefficients in C, indeed, that's C to the 2G. So if you like to think about this in terms of complex algebraic geometry, what's happening here is H1 under Hodge theory breaks up as the direct sum of two G-dimensional spaces. And let me see if I can remember which one is which. I believe this one is H1 of the structure sheaf. Let's see. Apologize, I didn't check beforehand what the conventions for Dobot cohomology are. So there's about a 50% chance that I got this wrong. And we can talk about that later. But yeah, that's what this sort of relation, one of the ways to think about this relationship to geometric genus. But this is capturing, right? If you think about this in terms of complex valued one forms, where this decomposition comes from is half of these are represented by holomorphic one forms, and half of them are represented by anti-holomorphic one forms. And the anti-holomorphic one forms correspond to classes in here. The other ones are sections of something. What are those sections of? So this is, sorry, I wrote the wrong thing here. This should be X structure sheaf. So here I said holomorphic one forms, just kind of assuming that you would know what that means. So we're going to use this later. I might as well just introduce it now. There exists a line bundle. Smooth K variety. Often called the canonical bundle. The dualizing sheaf. Etc., whose sections are holomorphic volume forms. I should say algebraic, or algebraic volume forms. If you were thinking about this in this kind of complex differential geometry world, I would really mean holomorphic volume forms. So of course, on a curve, this just means one form. So that's where sort of the other part of the topological cohomology is coming from. All right. Any questions? So this is sort of the chapter in Vacchial that will be sort of the first one we don't get to, is kind of carefully constructing this. basically using the construction of algebraic one-forms. So I'm not going to kind of explicitly prove to you that this exists, but especially on a curve, you can figure this out. You really just take df of functions and you think about how those change coordinates. And that tells you how to construct this guy. All right. Are there any questions about this stuff? Yeah. No, it's unique. It's called canonical. Come on. Yes, it's unique. We'll see in a moment. One of the various different ways to characterize it. Okay. So why did I introduce this guy? Because it's actually key for the question of, well, how do we figure out what this H1 is? We know that we can compute it using this, an affine cover using this check cohomology, but that's not really a very satisfying answer. And especially for curves, there's a really nice answer for how we should think about this. This is given to us by Serre duality. So assume X is smooth, irreducible, for an algebraically closed field. The algebraic isn't that important. It's mostly just so I don't have to say geometrically irreducible. And F is a locally free sheaf. And to do irreducible. Okay. I should have written projective. Dimension n. All right, so don't just want projective. Right, sort of the whole point is I'm going to try to use this to figure out when proper curves are projective. So it's bad if I assume that things are projective. Then the cohomology of F on X, so I have a locally free sheaf, I have cohomology on X is isomorphic to take the n minus I sheath cohomology of F dual tensor the canonical sheaf and take the vector space dual of that. I'll just mention you can also write this as sheaf hom from F to the canonical sheaf. So yeah, these vector spaces are dual to each other, right? Like you will often see this written as there is a perfect pairing from here to the field K. That's really kind of what you explicitly construct. Yeah, I mean, the isomorphism is natural because, let me go back to writing it this way. This is covariant in F, right? If I have a map from F to G, I get a map the other way on the dual, and then I take the dual of the vector space and I get a map the right way. So both of these are functorial in F in the same way. which is one hint to why you have to have another dual here. Yeah. Uh, this is your answer, right? It's from that sheaf to O of X. And I just want to emphasize this is the sheaf hom. Yeah. Yeah, well, apply Poincare duality to H1. It tells you there's a perfect pairing between these spaces, and you get this. So if you are thinking about a complex algebraic variety, then you can interpret this as like Poincare duality applied to the Dolbeau cohomology and how it sort of respects the Hodge decomposition. There's also sort of a more philosophical connection between them, because sort of both of them come from the fact that push forward has a left adjoint and a right adjoint. So, somehow where this canonical sheaf comes up, there is a version of this that works for all varieties. It comes from, you get the canonical sheaf by doing the left adjoint to push forward instead of the right adjoint. Wait, did I get that right? No. Sorry, switch that, reverse it. You take the right adjoint to push forward, which is different from the usual pullback. Yeah, I mean somehow in Poincare duality, for a smooth variety, you don't usually see this canonical sheaf coming up, because for a smooth map, or I should say a fiber bundle, the left and right adjoints to push forward just differ by a shift in the derived category, right? Whereas in coherent sheaves, they differ by the appearance of this canonical bundle. Right. Yeah. I mean, I think somehow what you're saying is on a non-orientable manifold, there's a canonical line bundle, which is not trivial. It's the line bundle of orientations, right? And so if you want Poincare duality in the sort of manifold case, you have to twist it by that line bundle. And in the orientable case, that line bundle is trivial and you don't notice that it's there. And again, I think you could sort of say all of this by going yada, 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 shriek pullback, right? So the key thing here is that in sort of both these settings, there's a shriek pullback that satisfies this. I keep putting this in the wrong place. That would be what a usual pullback satisfies. All right. And if you apply this with F, the map to a point, right, here you're getting from the cohomology into, and so I apply this with G equals K. You can add the map from your space to spec K. So this is fairly automatic. The interesting part is, why is this shriek pullback? Yeah, why is it this is the shriek pullback of that G? Yes. So, right, usual pullback is the left adjoint to push forward. So the kind of where all these duality theorems come from is that the left and right adjoints to pull back to push forward are similar but not the same. And this sort of weird canonical bundle business is always accounting for that difference. So, people would say that's where the degree shift in Poincare duality comes from. It comes from the fact that when you do Schrieg pullback, you don't get the constant sheaf, you get a shift in the derived category. And if your variety is singular, then you don't get the constant sheaf at all. You get some weird thing. All right. So there's lots of fun discussions to be had about generalizations of this. But in the case of curves, this is a really concrete statement that's very useful. Right? It tells us that if I want to understand H1, some line bundle L, that's isomorphic to H0 of L dual, tensor the canonical bundle. And of course, the canonical bundle is, I shouldn't use C, that would be bad. Is O of some divisor, right? So I could rewrite this as if I want to understand H1 of O of D, then I have to get that that's the same as H0. There's a vector space dual here. And if I just care about dimension, that's not a big deal. Minus D plus B. Vector space dual, but if I'm just worried about the dimensions, then I don't see that dual. So little h1 of O of D is equal to h0 of O of minus D plus B. Sorry? It's the divisor that corresponds, the canonical divisor, a canonical divisor. There isn't one. That just means you take a meromorphic one form and you look at the divisor it gives you. Okay. So in particular, right, when we had this short exact sequence where I look at O of minus P, L, skyscraper chief at P. I take the long exact sequence and I get H0 of L of minus P goes to H0 of L. So this just means I take a section of L that's required to vanish at T, and then I say, it didn't have to vanish at T. I have a copy of K here. I have the connecting homomorphism. And now I can write this next guy as L dual T plus this canonical bundle. So let me just write tensored with the canonical. Right. The dual of O of minus P is O of P. Oh, great. There's duals here. Great. Yeah. Okay. So actually, the other part of this long exact sequence is also this map of require something to vanish at a point, or this is sort of take a normal section and then allow it to have a pole at this point, right? And I get the map the wrong way because of these duals. But in particular, right, so this is saying that exactly one of L turning to L minus P turning to L, or L dual tensor the canonical bundle turning to L dual P tensor the canonical bundle gets a new section and the other one doesn't. This map, it's the right way because there are duals. So if I didn't have the duals, I would have a map this way, which is allow a pole. So when I take the vector space dual, I get a map in the right direction. Okay, so this K, right, this tells us one of these maps, either this map is surjective and this map is 0, or this map is 0 and this map is injective. So either way, one of these maps is an isomorphism, and the other one, well, again, this one is injective with co-kernel one-dimensional, or this one is surjective with kernel one-dimensional. So that's saying that exactly one of these things changes. So if one of them can't change, the other one has to, and vice versa. Now you might say, is that really that helpful? Remember, we're sort of trying to figure out when this changes because it's going to help us figure out when L is globally generated and when L is very anti. And there is a sort of good point at which you would know that this guy doesn't change. So note, if D is not effective, which means that when I write D as this sum of points, the coefficient of one of the points is negative. What does that mean? That means that every wait. No, sorry. No. I mean, that means that this can't be the divisor of a section. I have to be careful because that doesn't mean that every section of this guy is not effective. That's true, but there's a better thing to note. Note, if the degree of D is negative, then D is not effective. And in that case, sorry, now I've got this right. Every section of the line bundle has a pole. So this tells me every meromorphic, I should say rational section of O of D has a pole. Right? The degree is the sum of the number of poles with negative weights and zeros with positive weights. So if the sum is negative, there must have been a pole in there somewhere. So H0 O of D is 0. Okay, small extension of this. If the degree of D is 0, then the only way I could have a section, well, the poles and zeros have to balance out. So if I don't have any poles, I don't have any zeros either. So I get H0 of O of D is 0 unless D is trivial. I should say O of D is trivial, so it's isomorphic to the structure sheaf. Obviously, the structure sheaf has a section, but nothing else of degree 0 can have a section. All right. So if I choose my L so that this guy has degree 0, well, I've already killed all the sections, or sorry, negative degree. Then I've killed all the sections. And obviously, this map will be an isomorphism, so this one can't be. All right, the degree of the canonical bundle is 2G minus 2. All right, so that means that if I write this down, so the degree of L is greater than 2G minus 2, or actually if the degree is equal to 2G minus 2 and it's not the canonical bundle, then H0 of L is 0. Okay, so what does this tell us? Not H0, sorry. H0 L dual. So now L dual has degree less than minus 2G minus 2. So when I tensor it with the canonical bundle, this all has negative degree. So this has no sections. All right. So if the degree of L is greater than or equal to 2G, then what does that mean? That means that if I take H0 of L and I compare that with H0 of L minus P, I always get this equality. Let's be putting these as superscripts, right? Because I know that all of these H1s are 0 by this theorem, because this is the same as H0 of dual tensor the canonical bundle. This is dual. With a P, tensor the canonical bundle. So these, again, both have negative degree. So they're 0. So once I've made sure that these guys are 0, this sequence has to be exact. So it can sort of fail a finite number of times as I add more points to my divisor and kill off elements of H1 instead of getting new elements of H0. But eventually I will have used up all my elements of H1, and I will instead find that I've killed these, so I have to get that H0 is changing. Okay, so this implies that L is base point free. Right, this is a criterion for base point freeness we have already seen, which is if I take L and I remove a point, I lose a section. That's telling me there's a section of L that doesn't vanish at P. So similarly, we had characterized being very ample in terms of the change in the number of sections after I remove 2 points. So exactly the same proof. Shows that if the degree of is greater than or equal to 2g plus 1, then L is very ample. Hmm? No, it's not if and only if. Right, because I would have things with lower degree that already have vanishing cohomology. I think I can even have very ample things that have non-trivial cohomology, but not absolutely sure about that. Does it say that? Yes, but that doesn't tell you that the power you took was. I. It wouldn't surprise me if there was some vanishing theorem that proved this, but that one doesn't, right? That tells you that there's a power of this guy that has trivial cohomology, and we already proved that, but that's different.
Yes, for a very ample bundle. Show that so it's 0.
I mean, I have to admit, I would want to check. I didn't happen to confirm that point. Your argument has not convinced me thus far. But it wouldn't surprise me that much either way. I just don't happen to have checked recently. Okay. Now, what does this imply? This implies if L has positive degree, then L is ample. All right. So in particular, if I have a proper curve, it has an ample line bundle, or very ample line. But we've proven that proper smooth curves are projective. And furthermore, we've even produced a sort of simple way of finding an ample line bundle, right? If I just take a point and take 2g plus 1 times that point, I will get a very ample line bundle. And actually, I don't need smooth here. So one way to see this is actually if I have a finite map, and there's always a finite map from a smooth curve to any curve, if the pullback of a line bundle is ample, the line bundle was already ample downstairs. 2g plus 1, then I'm very ample. With 2g, I think this is, yeah, this is right, what we saw here, right, is that right? So the line bundles of degree 2G minus 1 already have vanishing first cohomology, right? So if I have degree 2G plus 1, then removing 2 points will give me something of degree 2G minus 1, which I still know has vanishing higher cohomology. All right. So now let's talk about what does this tell us? Well, for example, if I fix the genus of a curve, what kind of interesting things do I find by doing this? So if G equals 0, this implies that any, right? This tells us that any positive degree line bundle is very ample. So in particular, I have C of genus 0. I have any point in C, then O of P is ample. And sorry, I should say very ample. And of course, what kind of map does this give us? What embedding into projective space? Well, H0 of O of P, what is that? That's H0 of O plus 1, right? What I've found here based on genus G equals 0 is that all positive degree line bundles have vanishing cohomology. So in this case, this sequence always is exact. All right, well, that's 2. So I get a map of C to P1. Oh, sorry, but it doesn't matter. But yeah, you're right. And in fact, this map is a nice one. So we didn't sort of discuss this in great degree, but this notion of degree of a divisor also corresponds to the notion of degree of the map. Right? In particular, a very important interpretation of this is the given a map from some curve in P1. So this comes from a 2-dimensional linear series inside the sections of some line bundle. If the degree of L is D, then what does that tell me? That tells me that every element of P1 has D preimages up to multiplicity. And why is that? Well, to find the preimages of a point in P1, well, there's a unique section of O of 1 that vanishes at that point. I pull that back, that gives me a section of L which vanishes at exactly the pre-images. And one way to think about what I mean by up to multiplicity is when I pull back that section, which vanished to order 1 in P1, I have to pay attention to what order it vanishes on L. That's ramification. Including the generic point. So how do I interpret this as a statement about the generic point? Well, I look at the function field of C and the function field of P1, and this is a degree D extension. So sort of all of these notions which are called degree are all the same. So in particular, if I go here, this is a degree 1 map. I'm taking a degree 1 line bundle, and I get a map here. So this is a degree 1 map. So it has to be an isomorphism on the function fields. That's how you prove that this is actually an isomorphism. All right, note here, you can use a very similar principle to show that if I have a line bundle of degree 1 on C, C is not isomorphic to P1, then H0 of L is equal to 1. The reason being that if I had 2 sections, I would get a map to P1, it would be degree 1, and so it would have to be an isomorphism. You can also see this from Serre duality, that you sort of have to lose a section in, or have to lose an element of H1, so you can't be gaining an element of H0. So in particular, this implies that O of P is not isomorphic to O of Q for 2 different points. C is not isomorphic to P1. Yes, I mean not isomorphic. So the point is, if they were isomorphic, right, then that isomorphism would give me a 2-dimensional space of sections of this common line bundle. There would be one that vanished at P and one that vanished at Q. And then I could apply this argument to say, oh, my C was P1. Oh, sorry. Yes, sorry. Yeah, which is something that, for example, we had mentioned about elliptic curves. Right? We discussed this fact that if I have elliptic curves, I guess we'll have to talk about at some point in the makeup week, right, are G equals 1. So in that case, the canonical bundle is trivial. Right? I have to get that H1 of O is 1, right? And this gives me a section of the canonical bundle, which is degree 0. And so it tells me that it's actually trivial. So on an elliptic curve, I just have that h1 of O of D is h0 of minus D. So in particular, h1 of O of P is 0. So the only way the Euler characteristic can work out is if this guy is 1. All right, that's all we have time for. So we'll talk more on the 14th. So no class next week.